Okay, good afternoon. Right, so today, we want to continue with our introduction to computer uh, and finish the computer architecture topic. Okay, right. So far, under introduction to computer, we have finished introduction to computer evolution, and we are in the middle of computer architecture. So let's finish it today. Okay, let's finish it today. Right. So again, I will be using the note. I will just rush through the early part because we did it last time. Then we'll continue with and finish it. Okay. Right. So remember, computer architecture is all about understanding how the computer process your data. Okay. Computer is a data processing device. So initially, we look at the computer as a set of layers. So those things we have discussed. Okay. Hardware, firmware, system software, application software, and of course the users. Your data is initially entered through the application software and processed by application software, but in reality, your data is processed at hardware according to the instruction given in the software, so application software. So therefore, your data is set of ones and zeros, and you get the result as another set of ones and zeros, which is again interpreted and displayed as using your application software. Okay. And so that is the important thing you must understand. So then we look at overview of hardware, firmware, component of firmware, and of course the system software and application software. System software consists of operating system, system translators, and other utilities like file zip. And of course, the application software is your other applications, business or personal. And remember, computer represent everything as set of ones and zeros at hardware level. Anyway, we will be revisiting that in our next subtopic, representing data in computer. And so therefore, we look at what is bit, what is byte, what is mega, right? Giga, terabytes, and so on. 2 to the power 10, 2 to the power 20, and so on. Right, so then we moved on to hardware architecture, and we are in the middle of hardware architecture. So computer use component-based architecture for ease of manufacturing, ease of design, ease of troubleshooting, and so on, upgradability. And we use von Neumann architecture. According to von Neumann architecture, we have input devices, output devices, main memory, processor, secondary storage, tertiary storage, and ROM. Okay. And we discuss what are the purposes of each and every component. And of course, the motherboard does the coordination or facilitate communication among components. Okay. Right. So then we moved on to the storage organization. It's a hierarchy. At the top, you have the registries, which is part of the processor. So then you have the cache memory, your RAM, secondary storage like SSD or hard disk, and tertiary or backup storage like again pen drives, CDs, DVDs, external hard disks, and so on. And also we discuss in detail the caching mechanism. What is cache memory and why do we need cache memory? What is cache hit? What is cache miss? And even calculations about cache access speed. And also cache has level 1, level 2, and level 3. And also computer memory management we discuss. Computer can use part of the secondary storage as extension to your memory. So that is called virtual memory. So therefore, the logical memory is bigger than actual physical memory. Logical memory is the memory that your program see. It's not reality. But anyway, we will revisit this when we do operating systems. Okay. So you can think of memory as set of addresses and content, binary content. Each address can keep, say, 1 byte of data. And each data unit is a flip-flop or latch. We will look at what is flip-flop or latch when we do the fourth topic, data processing. Okay. Right. And also we discuss about the memory segments. Different memory address ranges are assigned to different tasks or different like one option. Portion is for OS, another portion for programs, another portion for data of the program, another portion for stack, another portion is the free area. And also we look at cache memory and how the caching, it always check the level 1. And if it is not found, level 2, if it is not found, level 3, and if it is not found, there also only RAM. But if you take something from RAM, it keep a copy in the cache so that next time it will be accessed fast. Right, so that is where we stopped. So last we discussed what is virtual memories. Okay. And now let's proceed from that point onwards. Actually, we are more than halfway. Right. So now we move on to the communication buses. So remember, computer use component-based architecture. So we have different components: processor, memory, secondary storage, right? Input devices, output. So we need some communication mechanism. Of course, it is facilitated by motherboard. And these communication lines are called buses. It's a funny word. So usually in roads, the buses are used for traveling, but in computing, these parts or roads are called buses. Okay, so therefore don't get confused. So that is the standard terminology we use. Okay, bus. Right. How does the computer communication buses are designed? It's something like lane road. You know that there are some, for example, Gold Road and so on. So we have lanes, maybe bicycle lane, bus lane, and for other vehicles. So similarly, if you take a bus or the main bus, which is between your processor and memory, so that is called system bus. And system bus are consisting of 3 lanes or 3 sub buses. Right? So we call them data bus, address bus, control bus. First of all, we have the system bus and IO buses. So system bus connect processor with memory. That is the main bus. So the major communication is in the system bus, because that is where data is transferring from memory to the processor, get processed, and the results are written back to the memory. Because processor communicate with memory, RAM. Processor does not directly communicate with your input devices, output devices, or secondary storage. So therefore, the major traffic is in the system bus. Then, of course, in order to communicate with peripheral devices like input devices, output devices, secondary storage, you have the input-output buses. Okay. So what is a bus? Communication line internally. So as I told you, you can look at the system bus that consisting of 3 sub buses: data bus, address bus, control bus. Okay, data bus, address bus, control bus. So remember, you can think of memory as something like you have addresses. Each address you can have, say, 1 byte of data. It's 001, say, set of data, which 00, so 0010, 11001011, 01. So this is address. This is your data or the content. Of course, when I say data, it can be data or programs. And remember, our system bus consists of 3 lanes. So 3 lanes are called data bus, address bus, control bus. So what is data bus? So data bus take these contents to and from, to and from. If your each memory address can have 1 byte of data, so then data bus width is also 1 byte. So that in one clock cycle, the entire content can be transmitted. So that is called data bus, which is used to send the memory contents from memory to the processor and processor to the memory. So then you have the address bus. Address bus is used to send these memory addresses only. Okay, memory addresses only. So therefore, address bus width is same as memory address width. If your memory address is 16-bit, your data bus, address bus is also 16-bit. If your data width for one particular memory address is say to 1 byte, then data bus width is also 1 byte. So that entire content can be transferred in a single clock cycle without breaking it to 2 or 3 parts. And finally, we have the control bus. So control bus is used to send binary control signals. Because we need to remember the process control unit also, arithmetic and logic unit, and control unit. So control unit generates certain controls to be sent to different components. And those control signals are sent through control bus. So now you must know what are the usages of these three sub-buses. Data bus is used to transmit these data or content of the memory address. Address bus is used to send these data memory addresses to and from. Control bus is to transfer control signals. For example, if the control signal might say, okay, save it or read it if it is sent to the memory and so on. Okay. Data bus, address bus, control bus. Right, so now we move on to another very important aspect, data processing. Any questions up to this point? Because no point me for move forwarding unless you have understood it. I hope you guys can understand this. Right, so how do we process data? Yes, at high level, we write our program. A Python program, Java program, C program, and according to the program logic, data is getting processed. So that is how we look at programming or program at high level or software level or application software level. But remember, the application software is under the control of the operating system. So operating system's task is get those processing required specified by your programming language through the hardware. So operating system will coordinate between program or systems, application software and hardware with the help of firmware. So therefore, at high levels, data processing is, yes, your marks and other things are getting processed by your programs, but at low level, set of ones and zeros are sent through logic circuits, and we get different set of ones and zeros, which is your result of the processed data. Okay. So your source code, Java code, Python code, and so on, which is high level, which is converted to something called assembly code, intermediate level, which is sort of a second generation low level language, but non-machine language. At runtime, this is further converted to machine code and executed. Machine code is the binary code. Okay. So I think this slide you are looking at in the second type because it's so important. You write your source code program, and in your program you represent data using variables and so on. But in reality, your program is translated to assembly and further translated to machine code at the runtime. Because ultimately hardware can understand machine code. Right. So keep that in mind. Keep that in mind. Very important. So then what is mean by processing at low level? So your hardware will apply either Boolean logic operations, binary arithmetic operations, bit of arithmetic things, bit of logic things. And then you have the information in binary, which your high level programs can interpret. Okay. Right. Get a feeling of this diagram is super important. Your high level program converted to assembly or the second generation code, which is further converted to machine code at runtime and executed. Right. Yes, at high level, we can think that your program, your data is processed according to the logic you have written in your Python code, Java code, C++ code, and so on. But it's intermediately converted to assembly code or the second generation programming code. And then it is further converted to binary code and executed. Right. So therefore, at high level, yes, your logic, your code, your if condition, else condition, while loops will determine how to process. But at low level, hardware level, your data is now set of ones and zeros. And those set of ones and zeros are getting converted to different set of ones and zeros. So that is what happens in hardware. Of course, we are more concerned about hardware layer. So at hardware, how does your data get processed? So we have already discussed this. Anyway, we'll revisit it. So your processor has a unit called ALU, arithmetic and logic unit, which is doing the processing. Okay. So your ALU consists of millions of logic gates, AND gate, OR gate, and so on. And your logic gates are made using transistors, hardware level transistors. Logic gate is concept, but the reality is transistors. I mentioned you that there are billions of transistors in different circuits in the modern i7 processor. Okay, billions of logic gates. And early days, we used to have vacuum tube based processing unit or the processor cells. But these days, we don't know we use vacuum tube. Rather, we use transistor based approach, but those transistors are very tiny and put it into integrated circuit. So therefore, overall hardware level data is processed by processor or any other system software. So this is how we used to build early days of logic gates using vacuum tubes. So we have a cathode having anode and cathode. So when you apply a small voltage, excessive electrons in cathode will move to anode. Okay. But this is old fashioned. So vacuum tubes had so many issues like high heat consumption, slowness, physically big and so on. So that is why computer engineers, electronic engineers came up with the idea of transistor-based gates. A transistor-based gate or logic gate. Forget about the logic part. So what is a gate? Gate is something we can open or close. When it is open, anything can flow. When it is closed, nothing can go through it. So the modern logic gates are made using a semiconductor materials like silicon and so on. So what is mean by semiconductor? Semiconductor is in between conductor and insulator. Not as good as conductor, but not as bad as when it comes to electricity flow, insulator. So semiconductor will allow with small voltage electrons to flow. With small voltage, not a huge voltage like vacuum tubes. Okay. So in the exams, they will never ask about how the transistor work, but it's good for your confidence if you are doing IT. Right. So to build transistors, you need, of course, consisting hundreds of transistors. You keep logic components, digital circuit components. Right. So you need semiconductor material like silicon, then dope in to make NO-P junction. So we introduce some foreign atoms to the left and right side of the junction. For example, possibly boron. It's a silicon lattice, silicon compound. Now, here you can see boron has less electrons than silicon. We call it a hole. Boron has less electrons than silicon. And if you take something like arsenic, it has more electrons than silicon. Okay. So when you lack electrons, so we call it positive charge. When you have excess electrons, because aluminium has extra electrons than silicon, so then we say it's negative. And under small voltage, electrons can go from negative side to positive side. So that is a gate. Gate is open, gate is closed. And then, of course, you can apply logic. Okay. So that is how modern semiconductor based or the transistors work. Okay, transistors work. So it's a junction, PN junction. Under small voltage, electrons can flow from negative to positive. Gate is open. When voltage is not there, tiny voltage is not there, gate is closed or zero. Okay. Right. So what are the advantages of transistor-based logic gates compared to the vacuum tube-based gates? Vacuum tube we use in 1960s. So the main advantage is it consumes very little electricity. It is super fast compared to vacuum tube-based gates. And also it's cheaper, less heat emission. It's a win-win situation, all positive points. So therefore, modern computers no longer use vacuum tube-based logic gates, rather use transistor-based logic gates. Okay, transistor-based logic gates. Right. So if you want to understand computer, if you want to do your ICT subject in a serious manner, you must have this confidence of knowing how the computer process data at low level. Okay. So you can find your logic gates as ICs. If you go to electronic shop, you can ask them, can I have an IC with 5 NAND gates, 3 XO gates? Those are not very expensive. And later on, you have a topic called Internet of Things, IoT, and digital electronics. So there we will further discuss about how to play with these devices with LED bulbs, batteries, resistors, and so on. Just remember, there are ICs with logic gates. But in computer microprocessor, of course, we don't use much ICs. Rather, your processor consists of built-in circuits. All these circuits are made of transistors. Okay. So your data going through logic gates are made using electronic gates based on transistors. Your data get processed. And there are circuit components like adders, multiplexers, encoders, which does either well-defined for sync tasks or controlling tasks. So we can combine these gates to build logic circuits. So that is our fourth topic actually. Sorry, not fourth, yeah. So third topic is representing data. Fourth topic is processing data at hardware level. That is digital circuits. So there we will further look at this. But for the time being, remember your data is represented as a set of ones and zeros. And those data going through different gates or circuits consisting gates. Okay. Of course, this is just I randomly draw it, but in reality, these are well designed logic circuit components like adders, encoders, decoders, multiplexers, and so on. So you will learn some of these logic circuit components in your fourth topic. Like what is AND gate, what is OR gate, what is XOR gate, and so on. But just remember, your data is sent through these circuit components to get it processed. Of course, when I say data, corresponding digital signal, okay, with digital signals corresponding to your data. So it results in different digital signal, and that is your final result in binary level. Okay, right. So this is super important to understand this. Super important. How things are happening. Okay, right. Right. As I told you, there are some logic circuit components which we can make using logic gates. Adders, some are doing processing, some logic circuit components are doing controlling actions, and some logic circuit components are used for memory as well. For example, your microprocessor has something called registries to keep the currently running instructions and related data. And those memory cells are also, registry cells are also made using transistors. So therefore, if someone asks for someone who is doing electronic or computer engineering or IT, what is the most important electronic device? No doubt transistor. Because transistors are used to make logic gates. And your computer is full of logic gates, circuits, components, especially your microprocessor. And even your registries are made of logic gates. Okay. Right. Right. So now we move on to processor architecture. And anyway, processor architecture is a very advanced topic, but in your A-level ICT, we just touch it. Right? We don't go into details because it's beyond your syllabus. Okay. So we just, at very high level, we look at the computer architecture or the processor architecture. Processor architecture means we are now more concentrated. Remember, last time we were more concentrating on the storage hierarchy. What is registry, what is cache, level 1, level 2, level 3 is SSD, and so on. But today we are more interested in processing. Representing data at low level and how the computer processes it. Okay. So what is mean by processing? Applying operations. What are the two type of operations? Arithmetic operations and logic operations. That is why we say that microprocessor has ALU, arithmetic and logic unit. Okay. So likewise, now you must have clear-cut answers. If someone asks what is mean by operations at hardware level, applying Boolean logic and doing arithmetic. And remember, arithmetic operations can also be done using logic. So therefore, ultimately, applying Boolean logic. So you get different set of ones and zeros, which can be interpreted as your final results. And when we apply these operations, so remember we are referring to the hardware and bit of software. So when we apply the operations, we can use control structures. Some operations are conditionally applied. Some operations we want to apply repeatedly, maybe 5 times or maybe until a particular condition is satisfied. So therefore, at a high level, what is we are processing? Applying operations based using control structures. Right. So if someone asks what is mean by processing, what is your clear-cut answer? At hardware level? Sorry, at high level, application software level, applying operations, that is logic operations and arithmetic operations, with the help of control structures. Some operations we need to apply conditionally, some operations we need to apply repetitively, and so on. Okay. But at low level, your data is set of ones and zeros, so signals consist in ones and zeros. And those data going through logic gates, and maybe again some other logic gate, and finally you get the process data. Okay. Right. Any questions? Because this is not an easy topic. Of course, if you feel it very easy, that is superb. But usually you must have some questions, doubts. So don't keep it with your mind. Just ask it and get it clarified. Right. So remember, we can look at the computer as application software, system software, firmware, hardware. So when we write programs, remember initially the data is processed by programs. So those are basically application software. Those are application software. When you write Java program, Python program, C program, C Sharp, you are writing applications software. Okay. So then you have the operating system, which is your main system software, firmware and hardware. Get processed and presented back. Okay. And these application software, which is these days very high level, but that is now 2024, we can write very high level application software. But in early days, programmers had no option but to write code in binary. First, we call it first generation language. Software developers or programmers, usually those days programmers used to be the people who develop the system, computer. And they needed to code using 1-0 level. And now these days we call it binary coding or machine level programming, which is very, very, very complicated task anyway. Machine code or binary code. So this is what computer engineers used to do in 1950s and early part of 1960s. Okay, machine code, 1-0 level programming, which is very difficult. But we had no other option at that time, 1950s, 60s. So only option was writing this. Remember, during the evolution of computer, we discussed that we used to input programs using punch card. So punch card is binary program. Punch card is a binary program. Right. So that is first generation. So then somewhere around 1970s and latter part of 1960s came the second generation languages. Second generation languages. So second generation languages are again low level languages. That means the programmer refer to the computer architecture and so on when he or she write program like memory addresses, register numbers, and so on. But it's a little bit of improvement because no longer you write 1-0 level code. You can refer to memory addresses and so on. And the most popular second generation language is assembly. Okay. Assembly language, which is not much used these days, but if you can, just have a look at it. And here we use English-like terms, still we refer to the computer architecture. Okay. Because it's a low-level language. And in 1970s, we moved to high-level languages. High level. That means we don't need to interested in hardware resources and so on. Of course, still hardware is used, but when you write the program, you don't need to think about the hardware. Okay. So that happens from 3GL above. And these are called high-level languages. Why? Because the hardware is not changed due to running programs. So languages like Java, C Sharp, C, C++, Pascal, those are all high-level languages or third generation high-level language. So not second generation, no first. Okay. So when you learn programming in when you learn programming in your topic, I think topic 8, right? Topic 8. Okay. So you will be learning Python. So Python is a 3GL language. It's a high-level language. What is meant by high-level language? You don't refer to the computer hardware. You don't refer to memory addresses. You don't refer to registry numbers and so on, which is very convenient without coding, without referring to the hardware. You can just concentrate on the problem solving, logical, program level. Still, you need to write the steps. This is how you are going to process it in third generation languages like Python. These are the operations you need to apply. Apply this in a loop, apply this conditionally. Okay. And then came fourth generation languages in 1990s. Fourth generation languages. So those are also high level, little bit higher than third generation. So here the main advantage is in third generation, though you do not refer to the hardware, still you need to write the logic, what to do. But in fourth generation language, you don't need to say, you don't have to say what to do. Sorry, how to do, even at high level, rather you can just say what to do, your requirement. Your requirement. So it's like giving instruction to a human. So just you tell your requirement. The intelligent human can do it. Right? So the most popular fourth generation language is SQL. If you want, you can even consider HTML, CSS as fourth generation, but only thing is those are not programming languages, markup languages, and so on. Okay. SQL is also not a programming language, it's a query language, but it's fairly fourth generation. So in SQL, you don't say how to get data from database, how to update a record in database, how to delete record in database. Rather, you just say delete it, insert it. Like for example, you can say delete from employee where employee ID equal 10. So this is like giving instruction to a person. It's very closer to the simple English also. So that is the beauty of fourth generation coding. You don't say how to do, rather you just say what to do. But only issue is these languages are not available everywhere. Of course, for query we have, but not for general programming like Java, C Sharp. So therefore, whenever you required, use it. But like SQL, we heavily use, but it don't think that this is going to work everywhere. Especially general programming, you don't need have fourth generation languages. Serious fourth generation languages. Okay. And now we talk about five generation also. So it's basically new trends like AI related things, fuzzy logic handling, and so on. Right. So while we were discussing about the hardware, we just look at the generations of programming languages as well. Right. So I think this is you are looking at you see this slide. I think maybe the fourth time because it's super important. So this is your high level program code like Python, Java, initially converted to assembly code and further executed to binary code and executed. Right. So we'll take a small break. After the break, we'll look at how does the computer processor process data at little bit high level, a little bit low level. How does your processor take an instruction, fetch it, decode it, execute. Then the next one is fetch, decode, execute. Fetch, decode, execute. Right. So we take a small break, and after the just maybe 7 minute break, and we'll be starting at let's say now 4:42, 4:50, 4:50 break. Okay. Just 8 minute break. Okay. So afterwards, after the break, we'll finish the computer architecture. Okay, computer architecture. So then we have very simple topics to finish the second. Okay. Right. 4:50 will start. Okay, so let's continue. Right. So now we look at, you know that your data is represented in 1-0 level, and those data is processed through logic gates. Okay. And your programming code, initially we do you write high level, then it is converted to assembly code like this, that is second generation, then converted to binary at the runtime. So therefore, you can see that your data is also a set of ones and zeros. Your instructions are also a set of ones and zeros. So that is very important to understand. Your data is low level, set of ones and zeros. Your instructions at low level, again, set of ones and zeros. Basically, each instruction is given a number. Add number, subtract a different number, multiply a different number. Okay. And control unit will generate different control signals to represent different processing steps. Add, subtract, and so on. Okay. So I told you computer is the most complicated device man has ever made. So therefore, this is not an easy task. And of course, we are at A level, we don't look at the 100% reality. We look at little bit simplified reality. And at very low level, your instructions are set of ones and zeros. Remember, your program is something like this now. Set of ones and zeros. And this is your instruction, and maybe this is your data part. Again, set of ones and zeros. So maybe one particular data, two particular data, sometimes even three data at binary. So binary instruction consists of your instruction and data. Okay, because and say this is my instruction 1, instruction 2, instruction 3 at low level. And one by one, say first instruction is fetch to the microprocessor, decode it, and execute. Then the next instruction is fetched to the microprocessor, decoded, execute. Then the third one, and so on, until your program is terminated or the processing is over. Okay, so fetch means remember your programs are also in the memory, right? When we say your data is in the RAM, actually your data and programs are in the RAM. So here the program means the binary programs. Binary programs. So first instruction is taken from memory to the microprocessor, decode, execute. Second instruction is fetch from memory to the microprocessor, decode, execute, and so on. And what is mean by decode? And after decode only, your AL you can or control unit can understand what exactly to do until it is not machine readable, 100% machine readable. After decoding only, the computer processor knows exactly what is the operation is, which part are operands or the data. Then only it can execute. And simply sometimes we call it fetch execute. Sometimes in your syllabus, mostly it's referred to as fetch execute, fetch execute, fetch execute. First one, second one, third one. But if you want to go a little bit more details, it's fetch, decode, execute, fetch, decode, execute, fetch, decode, execute. Okay. And these things happens in very high speed. Right. For example, a particular instruction can be fetched, decoded, and even executed within few nanoseconds. In next nanoseconds, the second instruction is fetch, decode, execute. Okay. Right. So don't try to understand this 100% because that is not possible at A-level ICT level. If you want to understand this perfectly, you need to do a degree where you have computer system subject. And even if you do IT degree, you don't get 100% idea. If you want to understand this 100%, you must do compute engineering or digital electronic engineering. So let digital electronic engineering, compute engineering people understand this perfectly. Our task is just get a feeling of it, get the big picture of it. Your data and instructions are both ultimately set of ones and zeros, which are resides in your memory when you run a program. And these instructions, binary instructions, are fetched to the processor, decoded, and executed. So execution is done by the ALU. And the control signals are sent by control unit depending on the processing step. And the input data is sent to the ALU. And the output data is again taken to the registries and later put it into the memory. And from memory, it is saved to the secondary storage, like your SSD hard disk. Okay. Right. So remember the microprocessor. Microprocessor means your processor or CPU. Your microprocessor has arithmetic and logic unit and control unit. Actually, registries are part of the ALU and control unit. So instructions, remember we have fetch, decode, execute. A particular instruction is loaded to one of the registries. And related data is also loaded to the registries. And then it is decoded. So once it is decoded, your control unit knows exactly what to do. Exactly what to do. So then your instruction is fed it to the ALU. Control unit will send the control signal saying what to do, and it is getting processed. So I told you that microprocessor has billions of logic gates. Those logic gates are inside the ALU. Okay. So try to understand it at high level, not exact detail level. Okay. So that is why we are building this understanding for last 3-4 weeks now. If you have any questions, you can ask. Again, you may not 100% understand, but still you may be having some questions, right? So that is fine. So then, no, I mean, that is fine means if you have any questions, just ask. But of course, you may not get answers to all the question in your mind because we don't go into great details in A level. But you must not have any obvious questions. Okay, obvious questions you must ask and clarify. So you can use the chat, you can talk, you can use the WhatsApp group, or you can just send me a personal message through WhatsApp. Usually I answer to each and every question. Okay. Now again, can you visualize what is happening? So this is your memory. RAM. Your RAM has the program and data. So each instruction is something like this. And partly instruction, partly data. And this kind of instruction is fetch from RAM to the processor. Or specifically, ALU has a special registry called instruction registry. So this kind of instruction is fetch from RAM to registry in ALU. Then this is your ALU. And this is decoded then. So this is fetch. Then it is decoded. So once it is decoded, it is machine readable. Your control unit can understand what to do. Okay. So then the relevant data is fed to the ALU. This is ALU, and the control signal is generated and sent. So control signal will say what to do with these data. Add it, subtract it, multiply it, do an operation, no operation. And the results are also temporarily written to a registry here. And then it is written back to the memory. So fetch, decode, execute. Then the next instruction is fetch. It is decoded. Once decoded, it is understandable for your ALU. Now it is executed. Relevant data is loaded and the control signal is sent, and according to that control signal, ALU will do the processing. And the results are written back to registries and then maybe to the RAM. So that keep happening. Fetch, decode, execute, fetch, decode, execute, fetch, decode, execute. And it is not always the next instruction, okay? Remember, your RAM has the machine instructions. Sometimes from this instruction, it goes to somewhere else, okay? Because there can be conditions, loop. In a loop, once you are at the end, again, it must come to the beginning. Again, you process, again, you come back, check the condition. So therefore, don't think that your instructions are always executed from top to bottom. Sometimes after this instruction may be here. And again, we are going back like this. That is why you have the control structures, if conditions, loops, and so on. So later on, you will combine these concepts together. Your understanding about computer architecture, your understanding about programming, okay, together. Then high level applications like web development. So when you combine these things together, you will get a better sense of what is computer and what is programming, what is information system, and so on. So you need a bit of patience. At the same time, if you have obvious questions, don't hesitate to ask and get it clarified. Okay. And your ALU has logic circuit components consisting logic gates. And you will further understand this when we do the digital circuit. That is not the immediate next topic. Immediate next topic is representing data and then logic circuit. Okay. So maybe after that, again, if you revisit these slides, you will better understand. You will definitely better understand these notes after finishing topic 3 and 4. It doesn't mean that here you don't try to understand it right now. Yes, try to understand here also. But after doing topic 3 and 4, again come back and read this note, definitely you will feel more comfortable. Because by the time you know exactly how the data is represented, exactly how data is getting processed at binary level. Okay. Right. So then in your motherboard, there's something called processor clock. Processor clock. And also when you buy a particular computer, usually you are interested in processor speed. First of all, you are interested whether it's i3, i4, and so on, or AMD, different versions they use. Yes, you are interested in that also, but you know that even though it's i7, maybe a particular processor is faster than another i7 processor. So that is called processor speed. Actually, what you mean by processor speed is processor clock speed. Processor clock speed. For example, in my computer, I have if I go to the task manager, you can check what is your processor clock speed also. Go to the task, right click in your taskbar and say task manager. Then go to performance and then go to CPU. And in my case, it is 2.8 gigahertz. You can see 11th generation Intel Core i7 at 2.8 gigahertz. So that is my processor clock speed. What is my processor clock speed? 2.8 gigahertz. Your one might be bigger, larger, or smaller. Gigahertz. So what does it mean? This is not bit, right? This is not bit byte. In bit byte, kilo means 2 to the power 10. Mega means 2 to the power 10, 20. Giga means 2 to the power 30. That is only when you work with byte. Just remember that, okay? So only when you work with bytes, kilo is 2 to the power 10 or 1024, mega is 1024 into 1024 2 to the power 20 and so on. But in all the other cases, kilo means 1000, 10 to the power 3. Mega means 10 to the power 6. Giga means 10 to the power 9. Okay? And this is not byte, so this is hertz. So therefore, giga means 10 to the power 9. That is 2.8 into 10 to the power 9 hertz. That is the clock speed of my i7 processor. And this is huge. 2.8 into 10 to the power 9 means 2, 8, and 8 zeros. One, two, three, four, five, six, seven, 8. So that is something like this. 2,800 million cycles per second. 2,800 million cycles per second. Do you believe it? Do you believe it? Right? So that means in a particular second, this much of pulses are generated. One pulse is something like this. So this is one pulse. So this is another pulse. And this is another pulse. So this one pulse, this is pulse 1, pulse 2, pulse 3, is generated 1 over these seconds, because in 1 second, this much of pulses are generated. You can think how fast it is. And it is so fast, and still we say, my computer is not fast enough. That is why you are going for next one, next one, next one, and you are looking for faster and faster process. Okay. So that is called processor speed means what? Clock speed. Clock speed means how many cycles per second. Right. 2.8 gigahertz means 2.8 into 10 to the power 9 cycles per second. So then what is the connection between this cycles per second speed and data processing? Remember, your data is in 1-0 level at hardware. So this data must be represented using a binary signal. And this binary signal is generated by altering this clock signal. Clock signal is just 1010 signal. Just remember it. Okay. Clock signal means clock is something in your motherboard that generate this kind of a regular signal. It's just 10, 10, 10, 10. And this is something like your clock is doing something similar to your heart is doing. Your heart. Can someone tell me what is the purpose of heart? Anyone? I'm asking simple question, right? What is the purpose of heart? No one? No one knows what is the purpose of heart. That is tragedy. Tragedy of our education system. Unfortunately. Yeah, to pump blood. So that pulse will pump the blood. Okay. So similarly, remember, if your data is in one place, it doesn't make any sense. Your data is just staying there. So what is mean by processing data? This data must be your corresponding signal for this data must go through logic gates, maybe NOT gate, maybe AND gates. Say this is one particular set of data. This is another particular set of data. So these data must go through gates, then it get processed according to AND logic, core logic, not logic, and so on. So therefore, in order to send these data, first of all, you need to generate binary signal like this that can be generated using this signal generated by the clock. And because the clock keeps generating the signal, it provides something like potential to transmit this data, this distorted or the, of course, no point sending 1010 signal through circuits. Like, first, you need to build this kind of a signal representing your data or set of signals, and then these signals must be sent. So when we say my clock speed is or process speed is 2.8 gigahertz, that means billions of these pulses can be sent within 1 second. So these pulses are generated and spent or sent through ALU logic circuits in super fast. And higher the processor speed, higher the feeding speed, higher the speed in feed of your signals, digital signals through the logic circuits. So that is what clock is doing. So now, do you have idea about what is system clock is? System clock generate this kind of a 10101010 pulse. And clock speed means, or processor speed means how many cycles in one particular second, which is usually huge, billions. And this regular clock pulse can be distorted to represent your data. And those data signals are transmitted through logic gates at hardware level and get a different set of signals, and those signals represent your results at binary, which can be interpreted by your high-level program as maybe set of text, set of audio, video, maybe beautified image, audio that has removed noise, or some text which is formatted, and so on, or some image which you have increased the contrast, and so on. Okay. So any questions? Now we are seriously into the computer architecture, how the computer process data. Okay. Right. Okay, so I just closed my PowerPoint. My mistake. Okay, so that is the purpose of processor clock, or sometimes we call it system clock. It's doing something similar task as your heart. Generate that potential for representing your data in digital signals and pushing it, sending it through different circuits, digital circuits. Okay. Right. So remember, your processor has arithmetic and logic unit and control unit. So arithmetic and logic unit is the one that does the processing. It has all the circuit components that does processing, like adding, subtracting, multiplication, division. Okay. Basically arithmetic operations and Boolean logic operations. But actually the Boolean arithmetic operations are also implemented using Boolean logic gate. When we discuss logic circuit designing, we will learn how to design a half adder, full adder using Boolean gates. Okay, that is why I told you that when you revisit this topic or note after completing the next two topics, you will in a better position to understand. But anyway, we need to start somewhere. It's like a chick and egg story. So you can't understand egg without chick. You can't perfectly understand chick without egg. So therefore, we want to first somewhat understand the chick can go to the egg, and then we come back and try to understand both together. Okay. But in our case, it's not just kick and egg. We have three topics: computer architecture, representing data in computer, digital processing data. We want to understand all three. When you combine all three, only you will get the best sort of understanding. Okay. And remember, in ALU, we have processing circuit units, right? Adders and so on, subtractors, and those are made of logic gates. And also we have registries. Registries are used to keep data, and registries are also made using transistors. So we call them flip-flops or latches. Okay. So therefore, your ALU is full of transistors, actually billions of transistor circuits. Right. So this is how you visualize as a logical thing ALU. So usually we use this particular symbol as a convention. And this is your input, maybe 2 or 3 inputs, so we call it operands. And then you get the results in binary, set of ones and zeros. Say this is my 1010 and 0111 as my data. And the control signal says add. Maybe add is another, say 00 is add, 01 is subtract, 10 is multiply. So say your control signal is 00, which correspond to add. And now your ALU's task is add these two numbers. Later you will understand how to add the numbers in binary. For example, but I will just show it. 0 plus 1 is 1, 1 plus 1 is 2, 2 means 0 giving 1, 1 plus 0 plus 1 is 2, 2 means 0 giving 1, 1 plus 1 is 2, 2 means 0 giving 1. So actually this is overflow because it's a 4-bit ALU. So therefore your output will be 0, 0, 0, 1. So these are your two inputs. Control signals correspond to add, assume 0, 0 is add. And this is your data result. And remember there's overflow here. And this is that overflow. So result is 0, 0, 0, 1, overflow 1. Don't worry, this is just to give you a bit of confidence, okay? So in the exams, they don't ask how these things are exactly happening, right? No, not at all. But remember when you go to exams, right? So I told you what you take is your confidence, your understanding, not your memory. So those who try to memorize things without understand, when the exams are nearing, so these guys have all the problems in the world, from headache. Sometimes when you get up in the morning, you are completely blank. Why? Due to pressure. So the pressure is with you if you try to memorize it without understanding. But if you're concentrating on understanding, forget about the exams, understanding. So then when the exams are nearing, you are more and more confident. Okay. Right. So therefore, so your data is fed. Your control signal will say what to do, and according to that, the data will be processed and the results are sent out. Okay. So remember, registries are also part of the ALU. And the good news is registries are also made using transistors. We call them flip-flops or latches. So registries keep your instructions at binary level and data at binary level. Sometimes results or the intermediate results of the processing. Later, those values in the registries or data registries will be written back to the memory through caches. And then the control unit. Remember, your microprocessor consists of ALU control unit. ALU consists of your ALU and registries and the decoder to decode. Okay. And control unit, as I told you, once you decode, your control unit can understand exactly what to do. Right? What to do. So then it will send the relevant control signal to the ALU. And the data is taken from here and the processing happens. So basically your ALU is under the control of control unit. Actually, not only the ALU, your entire computer is under the control of control unit, entire hardware. Okay. So therefore, control unit play a crucial role. Okay. And which control signals are sent depends on your program, high-level program, because it's a high-level program that converted to assembly code and then binary code. So that binary code represent your high-level code. Okay. So if someone asks what is the task of control unit, what is your answer? So control unit will interpret your machine instructions, especially after decoding. It knows exactly what to do, what is the processing step, and according to the processing step for the current instruction, control unit will send some control signals to relevant components like the ALU and so on. The ALU will do the processing based on the control signal received by the control unit, received from the control unit. Okay. Right. So now we are at the end of the topic. So final subtopic is, by the way, I'm keep asking this question. Do you have any questions? So don't let every question to be resolved by the time. කාලයට හැමදේම බාර දෙන්න එපා. Okay. Maybe some questions you want to resolve it to now itself. Okay. Now remember, when I did my A level, I did my A level in 1993. Right, 1993. No internet. Right. So of course, we had the tuition classes. So that is how we studied. So we go there, and then we come home. Right. So we have only the notes. Only the notes taken down. Okay. And we don't have smartphones, right? Smartphones, internet, nothing. Maybe we can go to the library and take 1 or 2 books as a supplement. But you guys, so therefore, if we have an issue, maybe we need to go wait until the next week to go to the tuition class and ask that question. So we never had WhatsApp groups. At that time, no internet. So that is how we studied. But you guys, so therefore, when we had a question, we had to keep that question for 1 week minimum. Okay. Even we never had chatting for discuss among students. But you guys, you don't have that problem, right? For example, if you feel like I need a little bit more details, right? Go to ChatGPT. Go to ChatGPT. Of course, you can specifically ask your question. Okay. You can even ask ChatGPT, please explain it in very simple manner. Okay. For example, you can please, or you don't have to say please. Okay. Explain how data is processed in the processor in simple and short way. And see whether you get a better understanding. You can see data in a processor works like this. Fetch processor gets the instruction from memory and see whether you have misunderstand something, whether the chat GPT is telling something other than what I am talking. It translates the instruction into actions it understands. No, now only it can understand. Now the processor can understand after decoding. It performs the required operation like math or moving data. Right? So then the ChatGPT says another step called store, that is storing the result in the registries or rather into the memory. So this cycle repeats rapidly to process data. So likewise now, when I did my A level, I had to ask this question. To ask this question again, I had to wait another 7 days because that is where we get the tuition, get back to the tuition class. So then maybe you can ask, so don't trust me all the time, right? Maybe you can suspect me also, right? Maybe this guy's answer clarification is not the perfect. Maybe this guy also doesn't understand this 100%. Actually, we doubted sometimes our teachers. Maybe our teacher is misunderstood this. So you can be like that also. Because we always thought that our generation is smarter than our teachers, our parents' generation. So you guys must also feel it like that. Challenge us. Don't always trust us. Okay. So let's see what is the purpose of processor clock in simple English. So that is how you get it. Simple English, simple and short. ChatGPT can understand. Right? The processor clock works like a timer that keep everything in sync. Actually, I did not explain that part yet. Okay. It sets the speed for how fast the processor can work, telling it when to start each step in the process, like fetching, decoding, executing. The faster the clock, the more instruction the processor can handle. Because faster the clock means what? Large number of bits are sent. Large number of bits are sent in logic gates. If this is 1 nanosecond, that is better than 2 nanosecond. So that means in a short time, this pulse is sent. Okay. And also I forget to mention about the synchronization. Actually, it's mentioned in your note, synchronization. Okay. So synchronization means all your instructions must be executed in a synchronous manner. Okay, synchronous manner. So I think that is mentioned here. You can see time synchronized operations and data transfer. Time synchronized. All these logic gates must be operating in synchronized manner. It's something like this. So this is how, so this is actually an example, very good example. So if someone want to explain how the computer processor work, okay, computer processor work, this is one explanation. Your computer processor at low level can only do arithmetic and logic operations, like add, subtract, multiply, and or XOR not. Of course, add, subtract, multiply is also ultimately and or XOR that combination. So therefore, some computer scientists, engineers use this example to explain computer to someone. You can think of computer or specifically processor, microprocessors, say, millions of kids. Why do we take kids? Because usually when you are in grade 5, 6, you can understand add operation, subtract, multiply, divide. Right? So you should be able to understand what is and, what is or, what is not. Okay. So therefore, we have millions of kids who are capable of doing these basic arithmetic operations and logic operations. Okay, billions of. So now you can think of what I am resembling as a kid. Anyone? possibly what I resembled as a kid, because this kid cannot do only arithmetic operations and logic operations, but actually arithmetic operations are also logic operations. So actually these kids represent something like a logic gate. So remember the microprocessor has billions of logic gates, and each logic gate contribute to logic operations, because logic operations are doing the arithmetic operations also. But these kids must do this in a time synchronized manner. So when these two kids do some processing and give it to this kid and maybe must do some other processing and give it to these two kids. But this must happen in a time synchronized manner, not their own time. Because these kids must be super fast doing processing millions of instructions in a second. So therefore, these guys can't do their own. For example, when these two kids finish their processing and give it to this guy must be ready to accept it. When this guy process it and give it to this guy, these two guys must be ready to accept and process. So this must be time synchronized. So very good example of time synchronization is, have you seen orchestra, music groups, orchestra? So we have violinist, right, pianist, right, someone who play guitar, and someone who play drum, right, set of people. Say about, in this case, this orchestra consists, it's not orchestra, it's consisting of kids doing arithmetic and logic operations, but they must do it in a synchronized manner, not their own time. So remember, in orchestra, we have something who control the orchestra, someone with a stick or something. So they all looking at this guy and do play their musical instrument according to the time. So that is why it's time synchronized. So therefore, your computer processor, you can think of it, not the musicians, kids doing capable of doing arithmetic and logic operations, but they are doing those things in a time synchronized manner. So that when this guy does some processing and give it to this guy is ready to accept it and do it. So it's happened super fast so that they can process millions of machine level instructions in a second. So that is how you understand. So this time synchronization is super important. This time synchronization happens according to the clock pulses. So clock pulse therefore has two usages. One is time synchronization. Second is providing the potential to generate the data signals. Okay. So therefore your pulse, your clock is acting like your heart, generating these regular pulses. At the same time, your clock is acting like this. So I don't know how to call this guy. Maybe you know the better name. Someone in the orchestra, controlling the orchestra, like a band master or whatever. Okay. So clock is time synchronizing, and clock is generating the basic pulse to, so that we can create the data pulses. Try to understand this. So the more you understand, the more you are confident. Right? You are confident. Otherwise, you will be lacking confidence. Right? And when the exams are nearing, those who have higher confidence, so they are happy. Others, they don't understand. So they try to memorize. So those who memorize without understanding, actually what you get is not confidence, you get stress. Closer the exam, higher the stress. But if you understand, the more you study, more you are comfortable, more you are confident, more you are happy. Okay, right. So now you must have a reasonable understanding about the role of the clock. Okay, processor clock. Right. So now we move on to our final subtopic, instruction set architecture, ISA. Okay, instruction set architecture. Just give me 1 minute. Okay, so let's continue. Right. So remember what we discussed is processor architecture. So if you want to explain your processor architecture, you must do something like this. So this is my processor. This is my memory, RAM, and my processor has ALU, some registries, control unit, registries, ALU, control unit. So these are your system. This is your system bus. Remember, system bus consists of three sub buses: data bus, control bus, address bus. Now your first instruction is fetch to the one of the registry. That is fetch. Then the decoder will decode it. So then only it is machine readable or understood by the control unit. Then control unit will send the control signal. And the data is fetch and getting processed. So that is execute. And the written results are written back to the registry, sorry, not the control unit, registry. And later it will be written back to the RAM. And from RAM, it will be written back to the secondary storage, which is secondary thing. So fetch, decode, execute. Again, fetch, decode, execute. So execution is controlled by the control unit, because after decoding, control unit can understand what to do and send the control signal. So remember, the controlling processing signal is also 1-0 signal, right? Once, so when the ALU get 11100, it knows that add, say 110111 maybe subtract. All these things are happening at binary level. Data is binary. Controlling is also binary signal. Okay. So that is called process architecture. How the data is processed at hardware level. With the help of RAM, or RAM is not doing processing, but RAM keep your program and data. That's your ALU, control unit, registries, and the decoder. Fetch, decode, execute cycles are happening until your program is fully processed or user has terminated, like close the program. Or exception happens and automatically program is terminated. Right, now we look at, so that is called process architecture, how the data is processed at low level, hardware level. So this subtopic is instruction set architecture, ISA. So this is sort of a logical level concept or abstract level concept of understanding computer, how the computer process data, how different computers process your data. Instruction set architecture. So instruction set architecture is part of the abstract model of computer. It's a logical thing. Abstract means logical thing. That defines how CPU is controlled by the software. Okay. How the overall processing is done. Okay. And your instruction set architecture explains what your processor is capable and how it is done. For the overall big approach. Overall approach of processing. So there are two instruction set architectures. Major. One architecture, one ISA is called reduced instruction set computer, RISC architecture. Some computers are CIS or complex instruction set computer. Computer means actually basically the process architecture. RISC processors, CIS processors. Okay. And most of the computers, especially our general purpose computers like laptops, smartphones, tabs, those are RISC. Actually, more than 90% of the computers are RISC processors, use RISC architecture. But there are some computers, especially very high-end servers, like database servers, web servers. So these servers, not always, sometimes or most of the time use CIS architecture, CIS instruction set architecture, or we call it complex instruction set computers. RISC computers or RISC architecture computers, CISC architecture computers, computer processors. Okay. So what is mean by reduce instruction set? Reduce means less. Instruction set means the supported machine level instructions. Machine level. So those instructions are very simple instructions like add, subtract, multiply, divide, and do, not, XOR, and some variations of and, some variations of not, and subtract, and so on. So in RISC computers, it supports small number of instructions, small number of machine instructions. Okay. So that is what is meant by RISC, reduce. So RISC computer processors support small number. That is what is by reduce number. And reduce number, small number of simple instructions, so simple machine instructions. But if it is a CISC computer architecture, it support large number of machine instructions. Why? Because it support both simple and complex instructions. Simple and complex instructions. So here only simple instructions, so therefore it's small number. But because here we have simple and complex instructions are supported, a relatively large number. If they support altogether, say 20, say 40 instructions, maybe this support 150 instructions, machine instructions. That means different variations of here maybe I have only add instruction. Maybe here we have maybe add 3 variations of add. Add 2 numbers, add 3 numbers, add 1 to the current number, so that we can do it in a special instruction. Okay. So RISC computers, for example, I will show you set of instructions supported by a particular RISC processor and CISC processor. So this is set of instruction, machine level instructions supported by a particular RISC processor. You can see just very small number of instructions. This is set of instructions, machine level instructions, binary level instructions supported by a particular CISC processor. CISC processor. Okay. And clearly you can see this one support maybe 20 instructions, maybe this one support 200 instructions. And here you can see there is only one, just for example, add operation. Sorry, 2 add operation, add and add C, sub and sub C. But here if you look at so many add operations will be there. You can see these are all add variations. Add C, add that, these are all add variation. So here just 2 add operations, but here about 10 add operations. So that is what is meant by here only simple instruction. Here both simple and complex variations of that particular add operation. Similar, if you have just one XO operation, maybe here some variations of XO operations. Okay. So therefore, CISC computers support large number of instructions because it supports some variations also. RISC computers support only the basic operation only. So therefore, small number of instructions are supported. Okay. And because RISC computers support only simple instructions, those instructions can be executed fast. Simple instruction can be executed fast. But complex instructions, maybe you need 2 clock cycle, 3 clock cycle to execute one particular complex instruction. So therefore, here we will be having more instructions because you don't have complex instructions. Here, lesser number of instructions, but one instruction may take more time. Here, one instruction take less time, but large number of instructions because complicated things must be done by multiple simple instructions. Okay. And because here only supports simple instructions, the instructions are pretty much fixed size. But here simple instructions, complex instructions, variations, so therefore instructions can be variable size. One instruction can be variable size because simple, mostly fixed size. And here one instruction can be executed in single clock cycle, but here complex instruction may take multiple clock cycles. And here a lot of code is generated because your program must be fully converted to machine instruction. So one particular statement may be executed by multiple simple instructions. So code is bigger. Generated machine code. Here generated machine code is short. So therefore here you may need more RAM. Here you may need only less RAM. And the other most important thing is these RISC computers are easy to design and manufacture because hardware level it supports only small number of simple instructions. But these more difficult to design and also develop. So therefore it's more expensive. More expensive. Okay. So RISC computers are cheaper because easy to design and manufacture. CIS computers, CIS processors are more complicated, therefore more expensive. And for general purpose tasks, RISC computers are good enough because we need cheaper processors. And also we are not doing very complicated processing, but maybe a very complicated processing, supercomputers, servers, maybe going for CISC is well, though the processor is more complicated and expensive, right? So do you have any questions about RISC versus CISC? So RISC support only small number of simple instructions, machine instructions. CISC support large number of both simple and complex instructions. So therefore, designing a RISC processor is simple compared to CISC. Therefore, it's cheaper, but performance-wise, little less. But that is okay for general purposes. So CISC computers, CISC processors, more complicated because it support large number of processors at instructions at hardware level. Therefore, it needs more logic gates and so on as well. But it does a little bit faster with the expense of complexity and of course the processors are more expensive. So that is what RISC versus CISC. Okay. So now we are done with computer architecture. Any questions? And this is the most challenging topic we have done so far. Okay. Of course, officially this topic is now over, but maybe you have some questions. So if you have any questions, I can answer. Because the next three topics are super easy. Right? Next three topics are super simple, just input output devices and so on. Okay. Maybe we can do two topics next time. Any questions? Because if you don't have questions, I can stop because we have a target for each day. We want to do this. And if you have questions, yes, I can take a little bit more time. But it doesn't mean that when you ask questions, it takes more time. No, I'm happy to spend 2 hours with you. But if you don't ask question means you are very comfortable. So maybe we can finish maybe 20 minutes, 10 minutes before 2 hours. Right. So again, I'm asking, do you have any questions? Right. Right. So make sure you do these quizzes, okay? In your Google Classroom. Introduction to computer, evolution of computer. So there are quizzes. Okay. So make sure you do all these quizzes by yourself, right? Don't expect me to do quizzes with you, right? You guys are no longer kids. So now you must have done following quizzes. For example, applications of ICT quiz you must have done. Okay. And social and economic environment, because we have done that topic. And ethics and legal aspects quiz you must have done. Introduction to computer quiz you must have done. Evolution of computer quiz you must have done. Okay. Computer architecture quiz now you can done. Now you can do. Today you can do. Okay. So do it. So doing quizzes is not my task because you guys have access to internet, Google Classroom. You guys are living in 2024. Okay. Right. So if you don't have any questions, we'll stop at this point. So the next class, we will be doing input output devices. Of course, it won't take more than 1 hour. So then we'll move on to storage devices, little bit more technically. Other thing is now you can again go through the syllabus and see whether what we have covered. Have we covered anything? Are we progressing? Okay. So go to A level. So remember the syllabus is available in your Google Classroom. The syllabus is available here, and see how much we have done and what kind of things we did today, because we have a specific target in our mind. Right? What have we done today? Right. So today also we look at right. So still we have not done these things. Input output devices, no. Not output devices and so on. Of course, the von Neumann architecture we have already discussed. Okay. So today we look at fetch execute cycle, or more specifically fetch decode execute cycle. And also we dig into the CPU. What is ALU? What is control unit? What are the registries? What is data bus? What is control bus? Right. Remember? We did not discuss what is multi-core processor. That we will discuss later. Okay, now see whether describe the stored program concept. That is von Neumann architecture. You load the program to memory. From memory, instructions are loaded to the processor one by one and executed. Fetch, decode, execute. Right. Name the major components of von Neumann architecture. That is input devices, output devices, memory, secondary storage, ROM, processor. Describe the fetch execute cycle. Now, can you describe it? If you can, you are done. Brief to describe ALU. This is your official A-level ICT syllabus, okay? From examine Department of Education. Briefly describes ALU, CU, memory registries, data and control buses. Draws the von Neumann architecture model and names its component. So that is input, output devices and so on. Describe the need of multi-core process. Still, we have not discussed the multi-core process. Okay. So multi-core processor means, for example, if I take my smartphone, my laptop, and go to CPU, it says 4 cores. So my computer, my processor is a 4 core. Remember, there are dual core processors. That is 2 cores. Octa-core processors, 8 cores. My one is 4 core. With logical processors, 8. Yes, logically 8 octa, but physically 4 cores. So we will look at that next time. Okay. And already you know what is L1 cache, L2 cache. Now, when you are going through your settings and so on, you must be more comfortable. That is what is the expectation, right? When you do ICT, you must be more comfortable with what computer. Okay. Right. So we have done those things. Right. We have done those things. Right. So memory hierarchy also we have done, but we will revisit these. Remember, we have the 2 topics: input, output devices, and storage. There we will go into these things more detail. What is PROM? What is EPROM? EEPROM? Right. And also we will revisit these different input devices, output devices, right? Different storage devices like what is CD? What are the variations of CD, DVD? How the hard disk work? How the SSD work? Right. And then your topic 2 is over. So topic 2 is over. Of course, it will take another 2 days to finish the topic 2. Then we will move on to topic 3, how to represent data, representing numbers in computer, representing characters in computer, representing audio, video, images, little bit. This is representing characters. So it's not a very big topic. So then you are done with topic 2. Topic 3. Topic 3 is not a big topic. Maybe we can do it in maybe 3 to 4 weeks. And then I told you logic. So I told you after doing the topic 3 and 4, you will be in a better situation to understand computer architecture, because still you have not fully understood how the data is represented. Still you have not fully understood how the data is processed in digital circuits. Right? So that is what topic 4 is all about. Different logic gates, logic related rules. What is De Morgan rule? What is identity rules? What are the commutative associative rules? How to simplify logic circuit using Carnot map, using those rules. what are the different logic circuit components, like what is an adder, right? Half adder, full adder, flip-flop. Remember, I told you registries are made of flip-flops, right? Registries are made of flip-flops. So how the registry work? So that is why I told you, once we do these things, you can revisit and better understand what is fetch, decode, execute cycle. Right? What is registry? What is ALU is doing? Because ALU has these components like adders. Okay. Then we will move on to operating system and so on. Okay. Right. So we'll stop at this point, right? Thank you.